mathematics often appears precise, logical, and orderly. Numbers follow rules. Equations balance carefully on both sides. At first glance, everything seems clear and predictable, but hidden within mathematics are problems that quietly challenge this sense of certainty. Some puzzles appear impossible when we first encounter them. They seem to contradict our expectations or lead us into strange conclusions that feel difficult to accept. These are the kinds of problems we will explore tonight, not as challenges to solve quickly and not as tests of intelligence. Instead, we will approach them slowly, almost like quiet landscapes of thought. Each puzzle reveals something subtle about logic, probability, infinity, or the limits of human intuition. Take a moment to imagine numbers stretching across a vast space, like stars scattered across a calm night sky. At first, they may seem random and distant, but with patience, patterns begin to appear, relationships emerge, structures reveal themselves gently over time. Many of the problems we will explore have puzzled mathematicians for decades, sometimes even centuries. Some have elegant explanations that unfold slowly once we understand the hidden assumptions behind them. Others remain mysterious, still inviting curiosity and reflection. What makes these problems fascinating is not only their solutions, but the journey of understanding them. Our minds often expect the world to behave in simple, straightforward ways. Mathematics sometimes shows us that reality is more subtle than that. Probability can surprise us. Infinity can behave in ways that seem almost dreamlike. Simple rules can produce patterns that stretch endlessly beyond our expectations. So tonight, there is no need to rush, no need to calculate or struggle. Simply listen, imagine, and let each idea unfold quietly. One by one, we will explore 20 mathematical puzzles that once seemed impossible and gently discover the hidden logic resting beneath them. Before we continue, if you like these types of deep thinking videos, please take a moment to subscribe and like so that we know that the YouTube algorithm is sharing the videos to the right people. Thanks. Imagine a hotel that stretches endlessly into the distance. Not a large hotel and not a very large hotel, but a hotel with infinitely many rooms. The hallway continues forever, each door marked with a simple number. Room 1, Room 2, Room 3, Room 4, and the numbering continues without end. This unusual place is sometimes called the Infinite Hotel. Now imagine that every room in the hotel is occupied. Every guest has arrived, checked in, and settled comfortably into their room. From room 1 all the way to infinity, every door is closed and every room contains a guest. In an ordinary hotel, this would mean the hotel is full. There would be no space for anyone new. A sign might hang quietly at the front desk saying there are no vacancies, but the Infinite Hotel does not behave like an ordinary hotel. Late one evening, a new traveler arrives at the front desk. The traveler asks for a room for the night. The hotel manager pauses for a moment and then smiles calmly. Even though every room is already occupied, the manager explains that space can still be made. The solution is surprisingly simple. The manager calls each guest and politely asks them to move to the next room. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3. The guest in room 3 moves to room 4. And this pattern continues endlessly down the hallway. Every guest simply moves forward by one room. Because the hallway contains infinitely many rooms, every guest can move without anyone being left without a space. And when this quiet rearrangement is complete, room 1 becomes empty. The new traveler is given room 1. The hotel was completely full, and yet a new guest was accommodated without anyone leaving. Take a moment to reflect on how unusual this feels. In everyday life, a full space cannot suddenly create room for someone new. If a theater has 100 seats and every seat is occupied, no new visitor can sit down without someone else leaving. But infinity behaves differently. Now imagine that something even stranger happens. Instead of one new traveler arriving, a bus pulls up in front of the hotel carrying infinitely many new guests. Each passenger would like a room. At first, this may seem impossible. The hotel already had infinitely many guests inside. Now infinitely many more have arrived. But once again, the hotel manager has a solution. This time, the manager asks every current guest to move to a room with a number twice as large as their current one. The guest in room 1 moves to room 2. The guest in room 2 moves to room 4. The guest in room 3 moves to room 6. The guest in room 4 moves to room 8. Every guest simply doubles their room number. This quiet shift leaves every odd-numbered room empty. Room 1 becomes available. Room 3 becomes available. Room 5 becomes available. Room 5 becomes available. And so on, endlessly. All the odd-numbered rooms are now open, creating infinitely many empty spaces. The new guests from the bus can now move into those empty rooms. The first passenger takes room 1. The second passenger takes room 1. The second passenger takes room 3. The third passenger takes room 5. And the pattern continues forever. Once again, the hotel that was already full has somehow made space for infinitely many new arrivals. This strange thought experiment was created by a mathematician named David Hilbert. It is often called Hilbert's infinite hotel. Its purpose is not to describe a real hotel, but to help us understand how infinity behaves. In ordinary arithmetic, numbers grow larger step by step. 1, 2, 3, 4. Each number follows the previous one in a steady sequence. But infinity is not simply a very large number, it is something entirely different. When we deal with infinite collections, many of the rules we expect begin to change. For example, if we take an infinite set of numbers and remove some of them, the remaining set can still be infinite. If we take all natural numbers and remove every even number, we are left with only the odd numbers. Yet, there are still infinitely many odd numbers. Infinity, in a sense, cannot easily be reduced, and it can sometimes grow without becoming larger in the way we expect. This is one of the quiet mysteries that mathematics reveals. At first, the infinite hotel seems confusing, even impossible. Our intuition tells us that a full space cannot hold more guests. But once we understand the structure of infinity, the puzzle becomes calm and logical. Every guest simply moves according to a pattern. No one disappears. No room is lost. The hallway simply stretches endlessly, allowing rearrangements that would never work in a finite space. Imagine walking down this infinite hallway. Door after door passes quietly beside you. Room 10, room 50, room 100, room 1000. The numbers continue climbing forever. Somewhere far ahead, guests are still moving to their new rooms. Some are doubling their numbers. Others are stepping forward by 1. And yet the hallway never runs out. This gentle paradox teaches us something subtle. Our intuition is shaped by the finite world around us. We are used to limited spaces, limited objects, and limited time. But mathematics sometimes invites us to explore ideas that stretch beyond those limits. Infinity is one of those ideas. It is vast, quiet, and strangely flexible. The infinite hotel reminds us that even when something appears completely full, new possibilities may still exist when we look at the structure more carefully. And perhaps that is part of the quiet beauty of mathematics. Even the most impossible situations can reveal hidden order, patiently waiting to be discovered. Imagine 3 travelers arriving at a quiet roadside hotel late in the evening. They are tired from a long journey and decide to share a room for the night. The hotel manager tells them that the room costs $30. The travelers each take $10 from their wallets and hand the money to the manager. $10 from the first traveler, $10 from the second, and $10 from the third. Together that makes $30. The manager accepts the payment and the travelers go upstairs to settle into their room. A few minutes later, the manager pauses and realizes something. There is a small discount available tonight. The room actually costs only $25, so the manager gives $5 to the hotel bellhop and asks him to return the money to the 3 travelers. The bellhop walks slowly down the hallway with the $5 in his hand, but as he approaches the room, he begins to think. $5 cannot easily be divided among 3 people. If he tries to give them equal shares, someone will receive an extra coin. After a moment of quiet consideration, the bellhop decides to keep $2 for himself and return $3 to the travelers. He knocks on the door and hands $1 to each traveler. Now let us pause and consider what has happened. Each traveler originally paid $10, then each traveler received $1 back. This means that each traveler has now paid $9 in total. $9 from the first traveler, $9 from the second, and $9 from the third. $9 plus $9 plus $9 plus $9 equals $27. But the bellhop kept $2. $27 plus $2 equals $29. And yet, the travelers originally paid $30. So where did the missing dollar go? Take a moment to notice how strange this feels. At first glance, it seems that $1 has quietly disappeared somewhere along the way. The arithmetic appears simple, yet the conclusion feels unsettling. But this puzzle is not actually about missing money. Instead, it reveals something subtle about how numbers can be arranged in misleading ways. Let us slowly walk through the situation again. The travelers paid a total of $30. The manager later decided that the room should cost $25, so $25 stays with the hotel. $2 was taken by the bellhop. $3 was returned to the travelers. $25 plus $2 plus $3 equals $30. Everything balances perfectly. No money has vanished. The confusion appears when we combine the numbers in the wrong way. Earlier, we said that each traveler paid $9. That part is correct. 3 travelers paying $9 each does equal $27. But this $27 already includes the $2 that the bellhop kept. The $27 is made up of 2 parts, $25 for the hotel and $2 for the bellhop. When we add the bellhop's $2 again, we are counting it twice. The puzzle quietly tricks our minds into combining numbers that should not be combined. Instead of adding the bellhop's $2 to the $27, we should subtract it. $27 minus $2 leaves $25, which is the amount the hotel kept. The arithmetic then makes perfect sense. 3 travelers paid $9 each, which equals $27. Of that $27, $25 belongs to the hotel and $2 belongs to the bellhop. Meanwhile, the $3 returned to the travelers simply reduced the original payment from $30 to $27. Nothing mysterious happened at all. And yet the puzzle feels convincing when we first hear it. This is because our minds naturally look for simple totals. When we hear numbers like 27 and 2, it feels natural to add them together. But in this situation, those numbers represent different parts of the same payment. Adding them creates the illusion that something is missing. This small puzzle reveals an interesting lesson about reasoning. Sometimes confusion does not come from complicated mathematics. It comes from arranging numbers in a way that quietly leads our thoughts in the wrong direction. Our minds often trust arithmetic automatically. If numbers are added or multiplied correctly, we tend to believe the conclusion must also be correct. But mathematics is not only about calculation, it is also about structure. Numbers must represent the right quantities before we combine them. If the categories are mixed together incorrectly, even simple arithmetic can produce strange results. Take a moment to imagine the travelers again, sitting quietly in their hotel room. Each one paid $9. Together their payments make $27. That money is already divided between the hotel and the bellhop. Nothing has been lost. Nothing has disappeared. The numbers simply needed to be arranged in the right way. This gentle puzzle reminds us that mathematics often asks us to slow down and observe carefully. When something seems impossible or contradictory, the answer is often hidden in the structure of the problem itself. With patience and quiet reflection, the confusion fades, the numbers settle into their proper places, and the missing dollar quietly returns to where it always belonged. Imagine a quiet television game show. The stage is simple. In front of the contestants stand 3 large doors. Each door looks identical, painted the same color, standing side by side under bright lights. Behind one of these doors is a prize, perhaps a new car. Behind the other 2 doors, there is nothing valuable at all. Only ordinary objects placed there to create suspense. The rules are simple. The contestant is asked to choose one door. Not to open it yet, but simply to point to the door they believe hides the prize. Let us imagine the contestant chooses door number 1. At this moment, the chance that the prize is behind door 1 is 1 out of 3. Another way to say this is that the probability is 1/3. This also means that the probability the prize is behind one of the other two doors together is 2/3. Now something interesting happens. The host of the show, who knows exactly where the prize is hidden, walks toward the other two doors. The host carefully opens one of them, always choosing a door that does not contain the prize. Suppose the host opens door number 3. Behind it there is nothing valuable, only an ordinary object placed there for the show. The audience watches quietly. Now, only 2 doors remain closed. Door 1, the door originally chosen by the contestant, and door 2, the only unopened door remaining. At this moment, the host turns to the contestant and asks a simple question. Would you like to stay with your original choice, or would you like to switch to the other unopened door? Many people feel that it does not matter. There are 2 doors left and 1 prize, so it may seem that each door now has an equal chance, 1 out of 2. But the mathematics quietly tells a different story. To understand why, we can gently walk through the possibilities. At the beginning, before any door is opened, the contestant chooses 1 door out of 3. This means there is a 1 out of 3 chance that the contestant has already chosen the correct door, but there is also a 2 out of 3 chance that the prize is behind one of the other 2 doors. This part is important. The original choice was made without any information, so most of the time 2 times out of 3, the contestant has actually chosen the wrong door. Now the host opens one of the remaining doors, but the host never reveals the prize. The host always opens a door that contains nothing valuable. This means the host is quietly giving us information. If the contestant originally chose the correct door, which happens 1 out of 3 times, switching would cause them to lose. But if the contestant originally chose the wrong door, which happens 2 out of 3 times, switching will lead them to the prize, because the host has already removed the other incorrect door. So by switching doors, the contestant wins whenever their first guess was wrong. And since the first guess is wrong 2 out of 3 times, switching gives a 2 out of 3 chance of winning. Staying with the original door keeps only a 1 out of 3 chance. Take a moment to reflect on how surprising this feels. Our intuition often tells us that once 1 door is opened, the situation becomes equal. 2 doors remain, so it feels natural to think the probability must now be 1/2 for each door. But the key detail is that the host's action was not random. The host deliberately avoided revealing the prize. This careful choice changes the structure of the probabilities. Imagine the game again, but with many more doors. Instead of 3 doors, imagine there are 100 doors standing across the stage. Behind 1 door is the prize. Behind 99 doors there is nothing valuable. The contestant chooses 1 door. The chance that this door hides the prize is 1 out of 100, very small. Now the host begins opening doors. One by one, the host opens 98 doors, each revealing nothing valuable. Only 2 doors remain closed. The contestant's original door, and 1 other unopened door. Now the question appears again: stay with the first door, or switch? In this situation, the answer feels clearer. The original door had only a 1 out of 100 chance of being correct. The other unopened door now holds the remaining probability, 99 out of 100. Switching suddenly feels like the natural choice. This larger example helps reveal the pattern that was already present in the 3-door version. The host's action gathers all the unused probability and concentrates it into the remaining unopened door. The puzzle is named after a television host named Monty Hall, who presented a game show where this situation often occurred. When the puzzle first became widely discussed, many people, including mathematicians, found it difficult to accept. Letters were written arguing that the probabilities must be equal. The idea that switching could double the chance of winning felt deeply counterintuitive. But careful analysis confirmed the result. Switching doors gives a probability of winning equal to 2/3. Staying with the original choice gives a probability of 1/3. This quiet puzzle reminds us that probability often behaves differently from what we expect. Our minds are comfortable with simple symmetry. 2 doors feel like equal chances, but probability remembers the earlier steps of the process. The original uncertainty never disappears. Instead, it shifts and concentrates as new information appears. Imagine standing on the quiet game show stage. Two doors remain before you. One choice holds a 1 out of 3 chance. The other holds a 2 out of 3 chance. The doors themselves look identical, but hidden behind them is a subtle structure of probability, a gentle reminder that mathematics often reveals patterns that our intuition cannot immediately see. Imagine standing in a quiet hallway inside a large house. On the wall in front of you are 3 simple light switches. Each switch can be turned on or off. They look identical, and there is nothing about their appearance that suggests which one controls which light. Somewhere far away in another room are 3 light bulbs. Each bulb is connected to exactly one of the switches. There is only one challenge. You may enter the room with the bulbs only once. Once you leave the switch panel and walk into the bulb room, you must determine which switch controls which bulb. After that single visit, you cannot return to the switches. At first, the puzzle feels difficult. If you simply turn on one switch and then walk to the other room, you will only see one light glowing. That tells you which switch controls that particular bulb, but it tells you nothing about the other 2. If you turn on 2 switches, then 2 bulbs will glow, but you will still not know which switch controls which bulb. And if you leave all the switches off, every bulb will appear dark. So how can you discover the correct connections with only one trip to the room? The solution comes from thinking carefully about information. Light bulbs do something interesting when electricity flows through them. They produce light, but they also produce heat. Even after a bulb is turned off, it may remain warm for a short time. This small detail becomes the key to solving the puzzle. Let us walk slowly through the solution. First, turn on the first switch. Leave it on for a few minutes. During this time, the bulb connected to that switch will begin to warm up. After a short while, turn the first switch off. Now turn on the second switch. Leave the third switch off. At this moment, one switch is off but was previously on. One switch is currently on. And one switch has never been on at all. Now walk into the room with the bulbs. Inside the room, 3 different clues will appear. One bulb will be glowing brightly. That bulb must be connected to the second switch, the one that is currently turned on. Another bulb will be dark, but when you gently touch it, it will feel warm. That bulb must be connected to the first switch, the one that was on earlier but was later turned off. The final bulb will be dark and cool to the touch. That bulb must be connected to the third switch, the one that was never turned on. With this simple method, the mystery is solved. Each switch has revealed itself through light and temperature. Take a moment to reflect on why this puzzle feels so satisfying. At first, it appears to be a problem about switches and wires, but the real solution comes from thinking about time and observation. The puzzle invites us to consider more than just what we can see. Instead of relying only on light, we also use warmth. Instead of observing a single moment, we allow time to create differences between the bulbs. This gentle shift in thinking opens the door to the solution. Many logical puzzles work in this way. They seem impossible at first because we limit ourselves to the most obvious information. We look only at what is directly visible. But when we pause and consider other properties of the system, new clues begin to appear. In this puzzle, heat becomes a quiet messenger carrying information from the past. The bulb that warmed earlier remembers that it once received electricity. Even after the light fades, the warmth remains for a while, silently telling its story. Mathematics and logic often reward this kind of patient observation. The answer does not come from complicated formulas or difficult calculations. It comes from understanding how the system behaves over time. Imagine again, standing in that quiet hallway. 3 switches rest on the wall. Behind distant walls, 3 bulbs wait silently. At first, the situation seems confusing, almost impossible to untangle. But with a small moment of insight, the system becomes clear. One switch leaves a glowing bulb. One switch leaves a warm bulb. One switch leaves a cool bulb. 3 switches, 3 bulbs, 3 different signals. This puzzle also reminds us that information can appear in unexpected forms. We often think of information as numbers, words, or visible patterns. But information can also be carried by warmth, motion, sound, or time. The world around us is constantly storing traces of what has happened before. In science and mathematics, recognizing those traces can reveal hidden structures. What first seemed like a mystery becomes a simple story waiting to be read. Imagine the bulbs once more. One shines softly, one rests in darkness but holds a quiet warmth, one remains completely still and cool. 3 small clues, each revealing a connection that was hidden only moments before. And with that, the puzzle gently resolves itself, leaving behind a quiet appreciation for the subtle ways information moves through the world. Imagine walking into a quiet room where a small group of people have gathered. Perhaps it is a meeting, a classroom, or a casual gathering of friends. Nothing about the room seems unusual. People talk softly, some sit in chairs, others stand nearby. Now consider a simple question. What are the chances that 2 people in this room share the same birthday? Most people begin with a natural assumption. Since there are 365 days in a year, it seems that we would need a very large group before a shared birthday becomes likely. Perhaps 100 people, or even 200. But probability quietly reveals something surprising. In a group of only 23 people, there is already more than a 1 out of 2 chance that 2 people share the same birthday. This result is known as the birthday puzzle, or sometimes the birthday paradox. At first, it feels difficult to believe. 23 people is a small group compared to the 365 possible birthdays. It seems like the odds should still be quite low. Yet the mathematics tells us otherwise. To understand why, we must shift the way we think about the question. Many people imagine the puzzle like this. What is the chance that someone in the room shares your birthday? That probability is indeed quite small, but the puzzle is asking something different. It asks whether any 2 people in the room share a birthday. Not necessarily yours, any pair at all. This change makes an enormous difference. When 23 people stand in a room, many possible pairs can be formed between them. The first person could share a birthday with the second, or with the third, or with the fourth, and so on. The second person could share a birthday with the third, the fourth, the fifth, and many others. Each pair creates a new opportunity for a match. When we count all these pairs, something interesting appears. In a group of 23 people, there are 253 different pairs of individuals, 253 chances for 2 birthdays to match. Each individual pair has a small probability of matching, but when many pairs are considered together, the overall probability begins to grow. The easiest way to understand the puzzle is to consider the opposite question. Instead of asking whether 2 people share a birthday, we can ask what the probability is that everyone has a different birthday. Imagine the first person in the room. They can have any birthday at all, so the probability that their birthday is unique is certain. Now imagine the second person. For the birthdays to remain different, the second person must avoid the first person's birthday. There are 365 possible days, and 364 of them would be different. So the probability that the second person has a different birthday is 364 out of 365. Now consider the third person. This person must avoid the birthdays of the first 2 people. So there are 363 acceptable days out of 365. The probability of remaining different continues to shrink slowly with each additional person. The fourth person must avoid 3 birthdays. The fifth person must avoid 4 birthdays. Each time someone enters the room, the number of safe days becomes slightly smaller. If we multiply these probabilities together step by step, we find the chance that all birthdays remain different. As the group grows, that probability gradually decreases. By the time we reach 23 people, the probability that everyone has different birthdays has fallen below 1/2. And that means the probability that at least 2 people share a birthday has risen above 1/2. Take a moment to picture the room again. 23 people standing quietly together. Each person carries a birthday somewhere along the calendar. At first, those birthdays seem scattered randomly across the year, but when we consider every possible pair, connections begin to appear. 2 people may share a birthday in January. Another pair may share a birthday in June. Someone else might share a birthday in October. The calendar slowly fills with overlapping moments. This gentle puzzle reveals something fascinating about probability. Our intuition often focuses on single comparisons. We imagine one person matching with another specific person. But probability considers every possible pair simultaneously. The more people there are, the more connections quietly form between them. It is like watching a web slowly weave itself across the room. At first, there are only a few threads, but as more people arrive, the threads multiply rapidly. Soon the web becomes dense with possible links. The birthday puzzle also reminds us that surprising coincidences are not as rare as they seem. When we meet someone who shares our birthday, it feels special and unlikely. But in a large world filled with many people and many interactions, coincidences naturally arise. Probability quietly explains how these moments appear. Imagine birthdays scattered along a long timeline stretching through the year. Each person places a small mark somewhere along that line. At first, the marks are far apart, but as more people add their birthdays, the marks slowly cluster together. Eventually, 2 marks land on the same day. The coincidence appears suddenly, yet the mathematics quietly predicted that it would happen. This is the quiet beauty of probability. It reveals patterns hidden beneath everyday events, and it reminds us that even simple questions can lead us toward deeper understanding of how chance and structure coexist in the world around us. Imagine holding a perfectly smooth sphere in your hands. Perhaps it is a small marble or a polished ball made of metal. Its surface is round and complete, containing a certain amount of volume. If we were to measure how much space it occupies, we would find a definite quantity. Now imagine something extraordinary. Suppose someone claims that this single sphere could be taken apart into a few pieces, and then those pieces could be rearranged to create 2 spheres that are each exactly the same size as the original. Not 2 smaller spheres, not 2 halves, but 2 complete spheres, each identical in size to the first one. At first, this seems completely impossible. If one sphere becomes 2 spheres of the same size, where does the extra volume come from? In everyday life, objects cannot simply duplicate themselves. If you divide a loaf of bread, the pieces become smaller. If you cut a block of clay, the pieces together still contain the same amount of material. But in the strange world of abstract mathematics, something remarkable appears. There exists a theorem known as the Banach Tarski paradox. It states that under certain mathematical conditions, a solid sphere can indeed be divided into a small number of pieces and rearranged into 2 identical spheres. Take a moment to pause with that idea, one sphere becoming 2 spheres of the same size. It feels less like mathematics and more like a magician's illusion. Yet this paradox arises from careful, logical reasoning within a particular branch of mathematics known as set theory. To understand how such a result could exist, we must first remember that mathematics sometimes explores objects that are far more delicate than physical matter. The pieces used in the Banach Tarski construction are not ordinary chunks of material. They are extremely intricate collections of points. These sets of points are so complicated that they cannot exist as physical objects in our world. They are mathematical structures that exist only within the rules of abstract logic. Imagine the surface of a sphere made not from metal or glass, but from infinitely many individual points. Each point has no size at all. It is simply a location in space. When mathematicians talk about dividing the sphere, they are really dividing this infinite collection of points into several groups. The remarkable discovery is that these groups can be moved and rotated in such a way that they form 2 complete spheres. Nothing is stretched, nothing is added. The pieces are simply rearranged. But how can this happen? The answer lies in the strange behavior of infinity. When infinitely many points are involved, sets can behave in ways that feel deeply counterintuitive. In ordinary geometry, shapes have well-defined volumes and surfaces, but when sets become infinitely complex, some of those familiar properties begin to break down. The Banach Tarski paradox depends on a principle called the axiom of choice. This principle allows mathematicians to select individual elements from infinitely many sets, even when there is no simple rule describing how the selection should be made. With the help of this principle, it becomes possible to construct extremely unusual sets of points. These sets are not measurable in the usual sense. That means we cannot assign them a meaningful volume. Without a well-defined volume, the usual rules about preserving size no longer apply. As a result, the pieces can be rearranged into shapes that appear to create new volume. But it is important to remember that this paradox exists only in the realm of pure mathematics. In the physical world, matter is made from atoms and particles. Objects cannot be divided into infinitely delicate point sets. If we attempted to perform this experiment with a real sphere, the material would simply break into ordinary pieces. No matter how carefully we cut it, we would never create two full spheres from one. The Banach Tarski paradox therefore tells us something profound about the difference between mathematical abstraction and physical reality. Mathematics is not limited by the properties of matter. It explores structures that are perfectly logical but not physically realizable. Imagine the sphere once more. Instead of a solid object, picture it as an endless constellation of points floating in space. Now imagine separating those points into several intricate patterns, each woven together in ways too complex to see. When these patterns are rotated and shifted, they combine again into new constellations. In this abstract universe of points, the paradox becomes possible. One sphere quietly becomes two. This idea can feel unsettling at first. It challenges our belief that size and quantity must always behave in familiar ways. But the paradox also reveals the extraordinary depth of mathematical reasoning. It shows that even simple shapes like spheres can hide unexpected mysteries when viewed through the lens of infinity. The Banach Tarski paradox reminds us that mathematics is not only about numbers and measurements, it is also about exploring the boundaries of logic itself. Sometimes those boundaries lead us into landscapes that feel almost impossible. And yet, within the rules of mathematics, they remain perfectly consistent. A quiet example of how infinity can transform our understanding of even the simplest shapes. Imagine a long, smooth shape that stretches forward endlessly, like the narrow bell of a trumpet extending into the distance. At the wide end, the opening is large and round. As the shape stretches farther away, it becomes thinner and thinner, slowly tapering toward a narrow point that never quite arrives. This curious shape is known in mathematics as Gabriel's horn. It is created from a very simple curve. The curve begins at a height of 1 and slowly slips downward as it moves farther along the horizontal direction. Mathematicians describe this curve with a relationship where the height equals 1 divided by the horizontal distance. When this curve is rotated around a horizontal line, it sweeps out a three-dimensional surface. The result is the strange trumpet-like form we call Gabriel's horn. At first glance, it appears to be an ordinary object. It begins wide and gradually narrows. The surface is smooth and continuous. But hidden within this shape is a surprising and almost impossible property. Gabriel's horn contains a finite volume, yet it has an infinite surface area. In simpler words, the horn can hold a limited amount of space inside it, but its outer surface extends endlessly. This idea can feel puzzling. Imagine trying to fill the horn with paint. The amount of paint needed to fill the inside is limited. A certain quantity will fill it completely, but if you try to paint the outside surface, you would need an infinite amount of paint. The horn could be filled, but it could never be completely painted. Let us explore why this happens. As the horn stretches farther into the distance, its width becomes smaller and smaller. Each cross-section of the horn forms a circle. The area of these circles decreases rapidly as we move farther along the shape. Because the circles shrink so quickly, the total space inside the horn gradually approaches a limit. Even though the horn continues forever, the remaining volume becomes smaller and smaller with each step. Imagine pouring liquid slowly into the horn. At first, a wide opening fills quickly. As the liquid travels deeper, the space narrows, and each additional portion fills only a tiny region. Eventually, the remaining space becomes extremely small. Mathematics shows that the total amount of liquid needed approaches a specific limit. In fact, the volume turns out to be equal to the volume of a cylinder whose radius is 1 unit and whose height is 1 unit. In everyday language, this means the horn holds about 3 1400 cubic units of space. The volume is finite, but the surface area behaves very differently. As the horn narrows, the circumference of each circular ring also becomes smaller. Yet the horn stretches endlessly. The shrinking circumference does not decrease quickly enough to prevent the total surface from growing without bound. Each thin section contributes a tiny strip of surface. There are infinitely many of these strips. When they are added together, their total grows without limit. The surface area becomes infinite. This result creates a quiet paradox. The horn can be filled with a limited amount of paint inside, but painting the outer surface would require an endless supply. Take a moment to imagine holding such a shape in your mind. You begin at the wide opening. The walls curve gently outward. As you move along the horn, the tunnel becomes narrower and narrower. Far in the distance, the shape continues, always shrinking but never completely disappearing. You could pour paint inside until it reaches the limit of the volume, but the outside surface keeps unfolding farther and farther. This strange behavior appears because of the way infinite processes work. When we deal with infinite sequences, two quantities can behave very differently even though they seem connected. The volume depends on how quickly the circular areas shrink. The surface area depends on how the circumference and length combine together. In Gabriel's horn, the shrinking areas reduce fast enough to create a finite volume, but the surface strips do not shrink quickly enough to keep the surface area bounded. The result is a shape that seems to defy ordinary intuition. Historically, this paradox fascinated mathematicians studying calculus, the branch of mathematics that explores continuous change and infinite processes. Gabriel's horn became an example showing how infinity can produce results that feel deeply surprising. The shape itself is perfectly consistent within mathematics. There is no contradiction in the calculations. Yet the conclusion challenges our everyday expectations. In the physical world, such an object could not exist exactly as described. Materials are made of atoms, and surfaces cannot extend infinitely while containing finite volume. But mathematics allows us to explore ideal forms beyond physical limitations. These ideal shapes reveal patterns and principles that deepen our understanding of infinity. Imagine once more the silent trumpet shape stretching endlessly through space. Its interior holds a quiet, limited space, but its surface continues unfolding farther and farther into the distance. A gentle reminder that infinity often behaves in ways our intuition does not immediately anticipate. And within these strange results, mathematics quietly invites us to see the world of numbers and shapes with new curiosity and wonder. One of the oldest and most famous puzzles about motion comes from the ancient Greek philosopher Zeno of Elea. Zeno lived around the 5th century before the Common Era, and was known for inventing paradoxes that challenged people's understanding of movement, space, and time. Among his many thought experiments, the most famous is the Achilles and the Tortoise Paradox, which questions whether motion is logically possible. The paradox involves the legendary Greek hero Achilles racing against a tortoise. Achilles is famous for being incredibly fast, while the tortoise is obviously very slow. To make the race interesting, Achilles generously gives the tortoise a head start. At first, this seems harmless. Of course, Achilles should win easily, but Zeno argues something strange happens when we examine the race more carefully. Imagine the tortoise starts 100 meters ahead of Achilles. When the race begins, Achilles runs toward the point where the tortoise started. Because Achilles is faster, he quickly reaches that spot. However, during the time it took Achilles to run those 100 meters, the tortoise has moved forward a little bit. Now the tortoise might be 10 meters ahead. Achilles then runs those 10 meters to reach the tortoise's new position. But again, during that time, the tortoise moves a little further forward. Perhaps now the tortoise is 1 meter ahead. Achilles runs that meter. Yet again, while Achilles covers that distance, the tortoise crawls forward slightly. Now the tortoise might be 1/10 of a meter ahead. This process repeats forever. Each time Achilles reaches the position where the tortoise was previously, the tortoise has already moved slightly ahead. The distances become smaller and smaller, but they never completely disappear. Achilles must first run the initial 100 meters, then the next 10 meters, then the next 1 meter, then the next 1/10 of a meter, then the next 1/10 of a meter, then the next 100th of a meter, and so on. Zeno points out that this creates an infinite number of steps. Achilles must complete infinitely many tasks before catching the tortoise, and completing infinitely many tasks seems impossible. So according to Zeno's reasoning, Achilles should never catch the tortoise. But of course, in the real world, we know that Achilles would pass the tortoise easily. A fast runner overtakes a slow walker all the time, yet Zeno's argument feels logically convincing. This tension between logic and observation is what makes the paradox so fascinating. To understand where the confusion comes from, we need to think carefully about infinity. Zeno assumes that because the race can be divided into infinitely many steps, it must take an infinite amount of time to complete them. But modern mathematics shows that this assumption is incorrect. Even though there are infinitely many steps, the total time required can still be finite. Let's imagine Achilles runs 10 times faster than the tortoise. The tortoise begins 100 meters ahead. First, Achilles runs 100 meters. Suppose that takes 10 seconds. During those 10 seconds, the tortoise moves forward 10 meters. Now Achilles runs those 10 meters. Now might take 1 second. During that second, the tortoise moves 1 meter. Next, Achilles runs 1 meter, which takes 1/10 of a second. During that time, the tortoise moves 1/10 of a meter. Then Achilles runs that 1/10 of a meter, taking 100th of a second. If we keep adding all these times together, something interesting happens. 10 seconds plus 1 second plus 1/10 of a second plus 100th of a second plus 100th of a second continues forever. The list has infinitely many numbers, but the total approaches a specific value. 10 plus 1 plus 1/10 plus 100th plus 1,000th, and so on approaches 11 1/9 seconds. In other words, even though Achilles completes infinitely many smaller and smaller steps, the total time remains finite. After about 11 seconds, Achilles reaches the tortoise and passes it. Modern mathematics describes this idea using something called a converging infinite series, which means an infinite list of numbers whose total approaches a fixed value. The steps go on forever, but the total remains limited. This idea was not fully understood until the development of calculus more than 2,000 years after Zeno lived. Ironically, Zeno's paradox helped inspire the creation of calculus itself. Mathematicians such as Isaac Newton and Gottfried Wilhelm Leibniz developed new mathematical tools for analyzing motion, change, and infinite processes. Their work showed how infinitely many tiny pieces could combine into a finite result. Yet even today, the paradox still feels strange when we first hear it. Our intuition struggles with infinity. When we imagine endlessly dividing space and time into smaller pieces, it seems as though motion should get stuck in an endless sequence of steps. But the mathematics of limits shows that these infinite sequences can still reach a final outcome. Philosophically, Zeno's paradox raises deeper questions about the nature of reality. Is space infinitely divisible? Is time continuous? Or does it come in tiny discrete units? These questions are still discussed in modern physics, especially in theories about quantum space and the structure of space-time. So, while Achilles clearly overtakes the tortoise in the real world, Zeno's paradox remains important. It reminds us that intuition can sometimes conflict with logic, and that understanding infinity requires careful mathematical thinking. Imagine a quiet, sunny field stretching endlessly before you. On this field lies a single grain of sand. Tiny, nearly invisible. It seems insignificant, almost nothing at all. Yet it is there, a discrete, measurable particle. Now consider a simple question. Is 1 grain of sand a heap? Most people would agree. No, it is far too small to form a heap. It is only a single grain. Next, imagine adding 1 more grain. Now we have 2 grains. Still, it is not a heap. Then 3 grains, 4 grains, 5. With each additional grain, nothing seems to change. 1 more, 1 more, 1 more. Slowly, almost imperceptibly, the pile grows. Eventually, after thousands or millions of grains, the pile clearly forms a heap. But at what exact moment does it become a heap? Is it at the 200th grain? The 1000th? There seems to be no clear boundary, yet intuitively, we know a heap exists once it reaches a significant size. This is the essence of the Sorites Paradox, also called the paradox of the heap. It was first discussed by ancient Greek philosophers such as Eubulides of Miletus, who wondered how vague terms like heap could be treated logically. The paradox arises because of two assumptions. First, one grain of sand is not a heap. Second, adding a single grain to something that is not a heap does not suddenly make it a heap. By repeating this reasoning, we conclude that no matter how many grains we add, we can never form a heap, and yet, plainly, heaps exist. Take a moment to visualize the field again. Grains are added slowly, one by one. The pile rises imperceptibly. The change is continuous and subtle. Our perception cannot pinpoint a specific threshold, but we recognize the transition intuitively. Something has shifted, even if no precise moment exists. Mathematics and logic approach this in various ways. In classical logic, statements are either true or false, black or white, but real life often contains gradual transitions. One grain may not be a heap, but a million grains clearly form a heap. In between, there is a continuum of gray area that challenges simple categorization. This paradox also has quiet philosophical implications. It reminds us that words and definitions can fail to capture the nuances of reality. Concepts that seem simple like heap, tall, or bald are not always sharply defined. Adding 1 grain, 1 millimeter, or 1 hair may not change a category, yet over many additions, the category does change. Some solutions rely on fuzzy logic, a mathematical system where truth values can range between 0 and 1 instead of being strictly true or false. In this framework, the truth of the statement, "this is a heap," gradually increases as more grains are added. 1 grain might have a truth value close to 0, 1,000 grains closer to 1/2, and 1,000,000 grains almost 1. Other approaches involve supervaluationism, where statements have truth values relative to precise but arbitrary cutoffs. The exact moment when the pile becomes a heap may be undefined, yet the reasoning remains consistent. Imagine standing beside the slowly growing heap. The grains shift quietly under your gaze. No single grain makes the difference. Yet after a long while, the pile is unmistakably a heap. The paradox is not in the physical world, but in the logic we use to describe it. The Sorites Paradox teaches patience, observation, and humility. It reminds us that some transitions are gradual and cannot be pinned down by simple rules. It shows that reasoning can be consistent and logical, yet still clash with intuition and experience. In life, we encounter many Sorites-like situations. Aging, learning, and growth all happen gradually. One day you are not old, the next day slightly older, then older still. No single moment marks the change, yet the passage of time transforms you. Mathematics and philosophy converge here, inviting us to notice subtleties, embrace vagueness, and recognize the limitations of absolute precision. The field lies quiet before you. Grains of sand shimmer under soft light. 1 grain is nothing. 2 grains are nothing. 2 grains are nothing. 2 grains are nothing. 3, 4. Each addition almost imperceptible. And yet, in the end, a heap rises. This is the quiet lesson of the Sorites Paradox, that small incremental changes can accumulate into transformations that defy simple description, and that infinity, vagueness, and subtlety are not obstacles, but invitations to think deeply and reflect gently on the world around us. Imagine a simple number sequence that begins with any positive whole number. Pick any number you like. For example, we could start with 7. The rules for the sequence are easy to follow, almost hypnotic in their simplicity. If the number is even, divide it by 2. If the number is odd, multiply it by 3 and then add 1. After applying the rule, take the new number and apply the same process again. Continue repeating this over and over. Let us take our starting number, 7. 7 is odd, so we multiply by 3 and add 1. 3 times 7 is 21, plus 1 makes 22. 22 is even, so we divide by 2. That gives 11. 11 is odd, so 3 times 11 plus 1 equals 34. 34 divided by 2 equals 17. 17 is odd, so 3 times 17 plus 1 is 52. Divide by 2 to get 26. Divide by 2 again to get 13. Multiply 3 by 13 plus 1 to get 40. Divide by 2 repeatedly to get 20, 10, 5, 16, 8, 4, 2, 1. Eventually, the sequence reaches 1. From that point, the sequence cycles. 1 becomes 3 times 1 plus 1 equals 4, then 2, then 1, over and over. This simple process is known as the Collatz sequence, named after the German mathematician Lothar Collatz, who first proposed it in 1937. What makes the Collatz sequence mysterious is not the process itself, but its behavior. Mathematicians have observed that no matter what positive whole number you start with, the sequence seems to always reach 1 eventually. Start with 2, start with 5, start with 1,000, start with 1,000,000 so far. The sequence eventually falls to 1 every time, yet no one has ever been able to prove that this is true for all positive whole numbers. The question remains unresolved, quietly puzzling mathematicians for more than 80 years. This simple rule has created one of the most famous unsolved problems in mathematics. To understand why it is difficult, consider the pattern of numbers. Some numbers quickly decrease to 1. Others grow very large before finally shrinking. For example, starting with 27, the sequence rises above 9,000 before eventually returning to 1. These dramatic fluctuations make it difficult to predict the behavior of the sequence mathematically. The Collatz mystery feels almost magical. A simple rule produces complex, unpredictable patterns, yet always seems to return to the same quiet endpoint. It reminds us that simplicity can hide profound depth. Imagine watching numbers climb and fall. Odd numbers surge upward when multiplied by 3 and incremented by 1. Even numbers fall rapidly when divided by 2. The sequence dances between growth and decline, yet the steps eventually converge on 1. Some mathematicians call this the hailstone sequence, because numbers rise and fall like stones bouncing on a hill. Each stone seems to leap unpredictably, yet eventually settles at the base. The problem has connections to deeper areas of mathematics, including number theory, dynamical systems, and computational complexity. Despite its apparent simplicity, the sequence eludes proof. It is a gentle reminder that mathematics can be both approachable and profoundly mysterious at the same time. Imagine sitting quietly with a sequence of numbers. Each step is simple to compute, yet the overall path forms a pattern that resists understanding. You might follow the numbers for hours, tracing their rises and falls, watching their rhythm, noticing how unpredictability emerges from simple rules. The Collatz sequence also offers a philosophical lesson. Life is full of simple rules that create complex outcomes. Small actions can lead to unexpected chains of events. Even the tiniest decisions may reverberate through a system in ways we cannot immediately predict. Mathematically, the sequence encourages patience, observation, and persistence. We can explore it for countless numbers without ever fully knowing its ultimate behavior, yet every exploration reveals fascinating patterns, surprising cycles and connections between numbers that feel almost meditative. From a distance, the Collatz sequence is quiet and repetitive, yet beneath its surface lies a labyrinth of complexity. Simple arithmetic creates intricate trajectories, demonstrating that even the most elementary operations can produce mysteries that resist resolution. Mathematicians continue to study the Collatz sequence using computers and abstract theory, testing enormous numbers, analyzing patterns, and searching for insights that might reveal why every starting number eventually returns to 1. Despite modern computational power, a full proof remains elusive. Imagine the numbers in your mind, rising, falling, twisting, and eventually collapsing to 1. The journey is unpredictable, yet the outcome seems inevitable. There is a gentle rhythm in the chaos, a quiet order hidden beneath apparent randomness. This is the Collatz mystery, a simple arithmetic process, easy to explain, impossible to fully prove, yet endlessly fascinating. It invites us to reflect on patterns, complexity, and the surprising depth hidden in even the smallest mathematical rules. The sequence reminds us that mathematics is not always about answers we can immediately see. Sometimes it is about the quiet exploration, the process of following numbers step by step, observing the intricate dance that emerges from simple rules and appreciating the subtle mysteries that lie beneath the surface of the ordinary. Imagine a shape drawn carefully on a piece of paper. A perfect circle, smooth and continuous, enclosing a space with all points equidistant from a center. It is a shape familiar to everyone, found in wheels, coins, and the sun itself. Now imagine a square. 4 straight sides of equal length, 4 right angles, perfectly symmetrical. A shape equally familiar, from windows to tiles, from books to doors. These two shapes are fundamental in geometry. They occupy space, they have areas, they have perimeters. Yet there is a fascinating and ancient problem that seeks to combine them in a way that seems impossible. The problem of squaring the circle. The question is simple to state: can a square be constructed that has exactly the same area as a given circle, using only a compass and a straightedge? These tools, used by mathematicians for thousands of years, allow for precise geometric constructions, drawing straight lines, perfect circles, and intersections. But no other measurements or calculations are allowed. At first glance, this seems like a reasonable challenge. After all, area is simply a number. For a circle, it is pi times the radius squared. For a square, it is the side length squared. If we can calculate these numbers, why not create a square of the same area? Yet the problem turns out to be deeply mysterious. The area of a circle depends on the number pi, which is the ratio of the circumference of any circle to its diameter. Pi is approximately 3.14159, but it is not a simple fraction. It is an irrational number, meaning it cannot be written as a ratio of 2 whole numbers, and its decimal expansion goes on forever without repeating. Because of this, mathematicians discovered that constructing a square of exactly the same area as a circle is impossible using only compass and straightedge. The tools of classical geometry are simply insufficient to capture the infinite, non-repeating nature of pi. This impossibility was proved in the 19th century by mathematicians such as Ferdinand von Lindemann. He showed that pi is a transcendental number, meaning it is not the root of any non-zero polynomial equation with rational coefficients. And because geometric constructions can only produce lengths that are solutions to such equations, squaring the circle is mathematically impossible. Despite the impossibility, the problem has fascinated mathematicians, philosophers, and artists for centuries. It represents the eternal human desire to reconcile the perfect roundness of the circle with the rigid straightness of the square, to unify what seems fundamentally different. Imagine holding a circle in your mind, smooth and infinite, and trying to fold it into a perfect square with equal area. The attempt is poetic, even if impossible. The circle's continuity resists being captured by finite lines and angles. It stretches beyond the reach of our tools. Throughout history, squaring the circle became a metaphor as well. Poets, writers, and philosophers used it to represent impossible tasks, unreachable ideals, and the tension between human aspiration and natural limitation. To square the circle became a phrase symbolizing the pursuit of perfection that cannot be achieved. Yet even in impossibility, there is quiet beauty. The process of trying, of exploring geometric constructions, of drawing circles and squares, opens the mind to relationships between shapes, proportions, and numbers. It leads to discoveries about algebra, calculus, and the infinite properties of numbers like pi. Take a moment to imagine drawing a circle with a compass. Smooth arcs meet at precise points. Then imagine attempting to draw a square of exactly the same area. Each side would need to be carefully calculated, yet the exact length cannot be constructed. It is always just out of reach. A subtle tension between ideal and achievable, between the abstract and the concrete. Mathematically, the problem also teaches about the boundaries of methods. Compass and straightedge constructions are a type of classical restriction. They allow only certain operations, drawing lines, drawing circles, finding intersections. Within these rules, some problems are solvable, others are not. Squaring the circle falls into the latter category. Philosophically, the paradox highlights the difference between measurement and idealization. Numbers can be infinitely precise, and shapes can exist perfectly in the realm of thought. but translating them into finite operations may be impossible. It is a quiet lesson about the limitations of tools, human or mechanical, in the face of infinite complexity. Yet mathematicians did not abandon the concept. They found approximate methods for creating squares that come very close in area to a circle. With careful calculation, one can draw a square whose area differs from the circle by a tiny fraction. These approximations honor the spirit of the problem, even if perfection remains unreachable. Imagine observing such an approximate square. Its sides almost match the circle's area. Place the square next to the circle, and notice how closely they align. There is satisfaction in the approximation, a gentle reminder that in mathematics, even impossible tasks can inspire creativity, insight, and beauty. The story of squaring the circle also encourages reflection on the interplay between simplicity and complexity. The question is easy to state, accessible to anyone who knows what a circle and a square are. Yet the resolution requires deep understanding of number theory, algebra, and geometry. The path from simple question to profound insight is long, winding, and quiet, filled with discoveries along the way. Standing back, we see the circle and square side by side. One smooth, infinite, continuous. One angular, finite, structured. They cannot be made exactly equal using only classical tools, yet they exist together in mathematics, inspiring thought and wonder. The circle whispers infinity. The square asserts finitude. The human mind reaches between them, exploring the subtle spaces where impossibility and beauty intersect. And in that quiet tension lies the enduring fascination of squaring the circle. An invitation to reflect, to wonder, and to appreciate the subtle harmony and limitations within mathematics. It is a gentle reminder that even impossible problems hold value. They expand our thinking, sharpen our intuition, and teach us to perceive the infinite, the abstract, and the subtly paradoxical in the quiet world of numbers and shapes. This is the story of the square and the circle, a paradox, a challenge, and a meditation, inviting us to see beyond the simple lines and curves and to experience the quiet majesty of mathematics itself. Imagine a small, quiet village tucked into the hills. In this village there is a barber, a man with a simple daily routine, trimming beards, cutting hair, and helping villagers maintain their appearance. On the surface, he seems ordinary, performing a very familiar role. But this barber is at the center of a curious and unsettling problem in logic known as the Barber Paradox. The problem is deceptively simple to state, yet it quickly leads us into strange and puzzling territory, the kind that quietly unsettles intuition and invites deep reflection. The paradox is often described like this. In this village, the barber shaves all and only those men who do not shave themselves. In other words, if a man does not shave himself, the barber shaves him. If a man does shave himself, the barber does not touch him. It seems simple enough, a rule defining the barber's duties clearly and efficiently. Now ask a question. Does the barber shave himself? At first glance, this may appear trivial. After all, perhaps he does, or perhaps he does not. But consider the rule carefully. If the barber shaves himself, then according to the rule, he cannot shave himself, because he only shaves those men who do not shave themselves. On the other hand, if the barber does not shave himself, then according to the rule, he must shave himself, because he shaves every man who does not shave himself. At this point, we see the paradox emerge. There is no consistent answer. If the barber shaves himself, he does not. If he does not shave himself, he does. No matter how we try to resolve the question, we encounter a contradiction. This paradox was formalized by the British mathematician and philosopher Bertrand Russell in the early 20th century as part of his exploration of the foundations of mathematics. Russell was investigating sets and membership, the question of which sets contain themselves and which do not. The barber is a metaphor for a set that contains all and only those sets that do not contain themselves. The paradox exposes a subtle tension in logic. It shows that certain self-referential definition statements that refer to themselves can lead to contradictions. The barber is defined in terms of shaving those who do not shave themselves, but the barber himself falls under that definition, creating a loop that cannot be resolved. Imagine the barber standing in front of his mirror, razor in hand. Does he shave himself? The question hovers in the quiet room. Every logical option leads to contradiction. The mirror reflects not just his face, but the limits of definable rules. The paradox is gentle in appearance, but profoundly unsettling in implication. Mathematicians solve this by refining the rules of set theory, by creating formal distinctions between different types of sets, and by forbidding unrestricted self-reference. The paradox disappears in rigorous mathematics. It teaches that language, definitions, and logic must be carefully structured to avoid contradictions. Philosophically, the Barber Paradox invites reflection. It illustrates how self-reference can quietly produce confusion. Even when everything seems simple, the paradox echoes through language, logic, and even everyday life, statements about themselves, systems that refer to themselves, and rules that include their own exceptions can lead to surprising and counterintuitive results. Consider the paradox in another form. Imagine a library cataloging all books that do not reference themselves. Which shelf should the catalog of all such books? The same tension arises. This shows the universality of the problem. It is not limited to barbers, mirrors, or shaving, but arises wherever self-reference exists in precise systems. The Barber Paradox also resonates with concepts in computer science. Certain programs or algorithms that call themselves recursively must be carefully designed to avoid infinite loops or contradictions. The quiet lesson of the Barber is that careful attention is required whenever a system refers to itself. Imagine the villagers watching the barber work, unaware of the subtle tension in his rule. The paradox exists not in the villagers or the barber's physical actions, but in the abstract structure of the rule itself. Logic quietly bends, revealing its limits. Despite the contradiction, the paradox is calming in a way. It invites reflection, meditation, and careful consideration. The mind can linger on the quiet structure of the problem, appreciating the precision, the subtlety, and the unexpected tension. It is a paradox to ponder slowly, gently, and without immediate need to resolve. Even in daily life, similar situations arise. Self-referential statements, instructions, or rules can create loops that feel impossible to satisfy. The Barber teaches us to notice these loops, to recognize patterns of self-reference, and to approach them with calm patience rather than frustration. From a mathematical perspective, the Barber Paradox encourages formal thinking. It demonstrates the need for careful definitions, distinctions between different types of objects, and avoidance of unrestricted self-reference. It quietly lays the foundation for modern logic, set theory, and theoretical computer science. Visualize the Barber once more, razor in hand, standing in a serene village, caught in a rule he cannot fulfill. His situation is impossible, yet it exists perfectly in the realm of thought. The paradox is a gentle, intellectual meditation on self-reference, infinity, and the boundaries of definition. It reminds us that mathematics and logic are not just about calculation or number, but about structure, clarity, and understanding. Even impossible scenarios have value. They teach us to see subtle patterns, to respect limits, and to appreciate the quiet beauty of abstract reasoning. The Barber Paradox concludes not with resolution, but with reflection. There is no answer to whether he shaves himself, yet the contemplation itself is instructive. It offers a gentle journey into the landscape of logic, infinity, and self-reference, a journey that is as calming as it is intellectually stimulating. In this quiet village, the barber stands still. The paradox whispers softly, some questions are not meant to be solved. They exist to guide thought, illuminate boundaries, and inspire a serene wonder at the curious structure of mathematics itself. Imagine a quiet path stretching endlessly through a forest. You take a step forward. Then the next step is determined by a coin flip. Heads, you move right. Tails, you move left. Each step is small, random, yet perfectly well defined. This is the essence of a random walk, a concept in mathematics and probability that reveals surprising patterns within apparent chaos. A random walk begins with a starting point, which we can call 0. At each step, a choice is made randomly forward or backward, left or right, up or down. Over time, the path meanders, twisting and turning unpredictably. Yet even in this randomness, Mathematics shows that certain patterns emerge, quietly hinting at order hidden beneath the surface. Consider the simplest case, a one-dimensional random walk along a straight line. Imagine you are standing at 0. Flip a coin, heads, move 1 unit to the right, tails, move 1 unit to the left, flip again. Repeat endlessly. Where will you be after 100 steps? 1,000 steps? 10,000 steps? The answer is both simple and surprising. Over many repetitions, the average position remains near 0. The path may wander far to the left or right, but the overall distribution follows a predictable bell-shaped curve called a normal distribution. The further you walk, the wider the spread, yet the center remains anchored at the origin. Now imagine a two-dimensional random walk. Instead of a line, you walk on a flat plane. At each step, you choose randomly to move north, south, east, or west. The path twists across the plane like a drifting leaf on a gentle stream. Over time, the probability of returning to your starting point remains high, yet the exact path is entirely unpredictable. Each step is independent, yet the cumulative effect follows statistical rules. Mathematicians have discovered fascinating results about random walks. In 1 and 2 dimensions, a random walker is almost certain to eventually return to the starting point. This property is called recurrence. In 3 or more dimensions, the walker may wander infinitely far away, never returning. The shift from recurrence to possible escape illustrates how dimensionality shapes the behavior of randomness. Imagine following a random walk in your mind. Each step is tiny, almost imperceptible. Yet as the steps accumulate, the path spreads across space. Peaks and valleys form in the probability of presence. Areas are visited repeatedly, while others remain untouched for long stretches. There is a quiet rhythm in this wandering, a subtle harmony emerging from pure chance. Random walks are more than abstract curiosities. They model phenomena in physics, biology, finance, and computer science. Molecules in a gas move randomly, producing diffusion. Stock prices fluctuate unpredictably, yet statistical patterns can describe long-term behavior. Populations of animals wander in search of food, following paths akin to random walks. Even the noise in electrical circuits and fluctuations in the stock market can be analyzed using this concept. Mathematically, a random walk is connected to probability theory, stochastic processes, and Markov chains, which describe systems evolving step by step with outcomes depending only on the current state. Each step in a random walk is independent of the past. Yet over time, the collection of steps forms predictable distributions, averages, and limits. Consider the one-dimensional walk once more. The expected position after n steps is always 0, yet the variance grows proportionally to n. This means that while the average remains at the origin, the possible distance traveled spreads wider as more steps occur. This delicate balance between stability and divergence is what gives random walks their quiet elegance. Visualize yourself taking step after step, guided by the flip of a coin. Each choice is simple, yet the sequence is unpredictable. You wander left, then right, then left again, tracing an intricate pattern across space. From a distance, the path may appear chaotic, yet statistical laws quietly govern its shape. Random walks also illuminate deep philosophical ideas about chance, unpredictability, and the interplay between order and chaos. Even in processes that seem entirely random, structure emerges. Patterns of return, distribution, and probability reveal hidden regularities beneath apparent disorder. In addition, random walks provide insight into infinite processes. Imagine extending the walk indefinitely. Step after step, coin after coin, the path continues without end. Yet mathematical tools allow us to analyze this infinite journey, predicting probabilities, expected distances, and return times. Infinity becomes manageable, ordered, and even meditative when approached through the lens of probability. Now picture a forest floor dotted with footprints, tracing a random walk. Some areas are visited repeatedly, others remain untouched. Over time, the pattern of footprints forms a soft, quiet map of motion, a tangible representation of chance interacting with structure. Each step is small, but the cumulative effect is vast, intricate, and patterned. Random walks also connect to the concept of Brownian motion, the jittery movement of particles in fluids, observed under a microscope. These microscopic paths mirror the steps of our abstract walker, showing that mathematics can describe both imagined sequences and physical reality with astonishing accuracy. Take a moment to consider the implications. A simple rule step randomly creates a path that is unpredictable in detail, yet governed by precise statistical laws. Randomness does not mean chaos. Infinite sequences of random steps reveal order, balance, and elegance. Each movement is independent, yet the overall shape is structured, like waves forming patterns on a calm sea. Philosophically, random walks remind us that life itself can resemble this process. Decisions, actions, and events may appear random, yet over time, patterns emerge. Small, independent choices accumulate to shape outcomes, distributions, and trajectories that are both surprising and orderly. Imagine following this journey quietly in your mind. Step left, step right, step back. The path meanders endlessly, each turn unpredictable, yet forming patterns that mathematics can describe. It is a gentle meditation on movement, chance, and the subtle beauty hidden in randomness. The random walk is a profound metaphor for infinity, probability, and quiet reflection. Each step, tiny and uncertain, contributes to a larger structure. Each choice, independent and simple, forms part of a grand pattern. And as the path unfolds endlessly, we see that chaos and order coexist, each step guiding us toward insight, curiosity, and calm contemplation. This is the quiet elegance of the random walk. Infinite in possibility, unpredictable in detail, yet structured and harmonious when observed as a whole. It teaches patience, reflection, and the subtle beauty of randomness, inviting the mind to wander gently along its endless, unfolding path. Imagine two identical twins, born at the same time, growing up together, sharing memories, laughter, and quiet evenings. One day, one twin decides to embark on a long journey into space, traveling at a speed close to the ultimate cosmic limit, the speed of light. The other twin stays on Earth, living a normal, peaceful life. When the traveling twin returns, an astonishing difference appears. The twin who remained on Earth has aged far more than the one who traveled. This is the famous Turing Paradox, a thought experiment that illustrates the strange and beautiful consequences of Einstein's theory of relativity. At first, the paradox feels impossible. Time seems constant, universal, and absolute. Seconds tick by identically for everyone. Yet modern physics tells us that time is not the same for all observers. The faster you move, the slower your personal clock runs relative to someone at rest. This phenomenon is called time dilation. It is not merely a theory. It has been measured in experiments, using precise atomic clocks aboard fast-moving airplanes and satellites. Let us examine the scenario in detail. Twin A remains on Earth. Twin B boards a spacecraft accelerating to a speed very close to the speed of light. As the ship moves faster, the passage of time for Twin B slows relative to Twin A. For every second experienced by Twin B, more seconds pass on Earth. Imagine the journey in 3 stages: acceleration, constant velocity, and deceleration. During acceleration, Twin B feels a gentle push backward into the seat. Time begins to slow slightly. Once the ship reaches near light speed, Twin B experiences time at a reduced rate, while signals from Earth seem to speed up. Twin B watches the Earth clocks ticking rapidly in the distance. Meanwhile, Twin A experiences time normally. Days, months, and years pass in a steady rhythm. Letters, messages, or signals from Twin B may take a long time to arrive. From Twin A's perspective, the traveling twin's journey seems extended and complicated. During the constant velocity phase, the effects of time dilation are most pronounced. If the ship travels for what feels like 1 year to Twin B, perhaps 10 years pass for Twin A. The faster Twin B moves, the greater the difference. The mathematics is precise. The time experienced by the traveling twin equals the time elapsed on Earth multiplied by the square root of 1 minus the ratio of the ship's speed squared to the speed of light squared. In simpler terms, the faster you go, the more time slows for you relative to someone at rest. This is not perception. It is a physical reality of space-time. Time is flexible, dependent on motion, and intimately connected with space. When twin B decelerates and returns to Earth, the differences become obvious. Twin A has aged significantly, perhaps decades, while twin B has aged only a few years. The paradox arises because it seems like each twin could view the other as moving. Why doesn't symmetry imply both twins age equally? The answer lies in acceleration. Twin B's journey involves leaving Earth, turning around, and decelerating to return. These changes break the symmetry, distinguishing the traveling twin's experience from the twin at rest. This paradox is a quiet invitation to imagine the universe in a new way. Time is no longer a universal river flowing identically for all. It bends, stretches, and contracts depending on speed and gravity. Space and time are intertwined in a four-dimensional fabric called space-time, and motion through this fabric affects the passage of time itself. Consider a visualization. Imagine a clock moving along with twin B. The hands turn slowly relative to clocks on Earth. Signals from the clock are sent back, appearing compressed or delayed depending on relative motion. The effect is subtle at ordinary speeds, but becomes dramatic as the velocity approaches the speed of light. The twin paradox also has philosophical implications. It challenges our intuitive understanding of reality, aging, and the passage of time. We often perceive time as absolute and consistent, yet physics shows that these assumptions are limited. Time, like space, is relative, shaped by motion and gravity. The universe does not conform to everyday intuition. It unfolds according to deeper, subtler principles. Imagine the twins reflecting on their experiences. Twin A watches decades pass comfortably, seeing the world change gradually. Twin B experiences a compressed, rapid journey, encountering only a few years of change. Their perspectives differ dramatically, yet both are internally consistent. Reality accommodates both viewpoints without contradiction. This paradox also illuminates the broader consequences of relativity. GPS satellites orbiting Earth experience time slightly faster than clocks on the surface due to weaker gravity and high orbital speeds. Engineers must account for time dilation, otherwise positioning errors would accumulate rapidly. The twin paradox is not merely theoretical. It has practical consequences for technology and navigation. Mathematically, the scenario can be expressed using Lorentz transformations, which relate space and time coordinates between moving observers. These transformations show how lengths contract, time dilates, and simultaneity shifts depending on velocity. Although the formulas may seem abstract, they describe a reality we can measure and observe. Take a moment to imagine the journey from twin B's perspective. Stars streak past the windows, distances contract along the direction of motion, and time flows gently yet differently than it does on Earth. The experience is serene, almost meditative, despite the dramatic consequences on return. Even though the paradox challenges intuition, it is entirely consistent within the framework of special relativity. The mathematics aligns with observation, and experiments with fast-moving particles and atomic clocks confirm the predictions. Physics provides a precise, reliable guide through what initially seems like a paradoxical situation. Philosophically, the twin paradox encourages reflection on the nature of reality. It shows that the universe contains hidden subtleties that defy common sense, yet operate with quiet precision. It reminds us that our everyday experience is only a slice of a larger, more intricate structure, where space, time, and motion are intertwined. Imagine the twins reunited. One has lived decades, the other only a few years. Their memories, experiences, and perspectives differ, yet both are equally real. This reconciliation mirrors the underlying harmony of the universe. Relativity does not create contradiction, it reshapes understanding. The twin paradox teaches patience, imagination, and a gentle awareness of the subtle principles that govern reality. It invites us to explore space-time, to follow journeys at near-light speed, and to reflect on how motion, speed, and perspective shape the experience of time itself. It is a quiet meditation on the flexibility of time, the beauty of relativity, and the astonishing consequences of moving through the cosmos. Just as the universe stretches and bends, so too does our understanding, encouraging curiosity, reflection, and a calm appreciation of the profound mysteries woven into the fabric of existence. In this thought experiment, paradox and clarity coexist. The twins' experiences differ, yet the physics is consistent. The journey invites contemplation, allowing the mind to wander through space-time, observing the subtle dance of time, motion, and perspective, and discovering the gentle elegance of the universe itself. Imagine sitting quietly in a dimly lit study, a stack of books around you, each containing carefully reasoned statements, proofs, and logical arguments. You open one and wonder, can every mathematical truth be proven within a single system? For centuries, mathematicians hoped the answer was yes. Yet in the 20th century, an astonishing discovery revealed subtle boundaries to reason itself. This is the story of Gödel's Limits, an exploration of incompleteness, subtle paradoxes, and the quiet mysteries hidden in the foundations of mathematics. Kurt Gödel, a brilliant Austrian logician, introduced his incompleteness theorems in 1931. His work challenged the dream of a perfectly complete and consistent mathematical system, a system in which every truth could, in principle, be proven from a finite set of axioms using logical deduction. Gödel's theorems quietly demonstrated that such a system is impossible for any sufficiently powerful framework, including the arithmetic of whole numbers. To understand this, imagine a mathematical system as a carefully constructed language. Within this system, symbols, rules, and axioms allow mathematicians to build proofs, deduce truths, and explore numbers with precision. The system is intended to be both complete, all true statements can be proven, and consistent. No contradictions exist. Gödel's first incompleteness theorem states that in any system powerful enough to describe basic arithmetic, there exist statements that are true, yet cannot be proven within that system. These statements are carefully crafted to reference themselves in a subtle way, analogous to the sentence, "This statement is unprovable." If the system could prove the statement, a contradiction would arise. If it cannot, the statement is true but unprovable. Consider the quiet elegance of this idea. Mathematics, often regarded as absolute and unassailable, contains truths that lie beyond formal proof. There are statements that the system cannot confirm or deny. They exist silently, true yet inaccessible, like hidden stars behind clouds in a night sky. Gödel's second incompleteness theorem deepens the mystery. It shows that no sufficiently powerful system can prove its own consistency. Even if the system is free from contradictions, it cannot demonstrate this fact purely within its own rules. The certainty mathematicians sought is limited. A quiet boundary exists, a horizon of logic itself. Imagine trying to peer beyond this horizon. Any attempt to see further requires stepping outside the system, using reasoning from a higher or external framework. Even then, truths remain elusive, subtle, and sometimes paradoxical. The limits are not failures of thought but intrinsic features of formal systems. These results have profound implications beyond mathematics. They touch on philosophy, the nature of human reasoning, and the limits of knowledge. Logic, while powerful, is not omnipotent. There are truths that exist quietly, beyond deduction, waiting for reflection rather than proof. Visualize the process. You construct a formal system, a lattice of axioms and rules. Within this lattice, you can explore many truths, deducing consequences and building intricate structures. Yet some statements lie at the edge, like faint, unreachable notes in a vast symphony. They are true but resist formal demonstration. They remind us of subtle limits woven into the very fabric of reasoning. Gödel's theorems also influence computer science. The idea that some problems cannot be solved algorithmically mirrors the notion of unprovable truths. Certain questions, no matter how rigorously approached, will remain undecidable within the constraints of a given computational framework. The quiet parallels between logic, mathematics, and computation reveal the depth and interconnectedness of these disciplines. Consider the philosophical resonance. Human thought can recognize truths beyond formal systems. Intuition, insight, and creativity allow the mind to grasp patterns that cannot be fully encoded in axioms. Yet even human reasoning may encounter its own Gödelian limits, reminding us of humility and the subtle boundaries of knowledge. Imagine a statement within arithmetic that claims its own unprovability. It sits quietly among the natural numbers, neither false nor provable. You ponder it, tracing its implications, and recognize the delicate tension it introduces. The system continues to function, consistent in its rules, yet always aware of its own limitations. This quiet tension is not discouraging, it is meditative. It invites reflection on the nature of truth, the structure of reasoning, and the vast uncharted territory that lies beyond formal deduction. Mathematics is no longer merely a fortress of certainty. It is a landscape with edges, horizons, and hidden depths, waiting to be explored with curiosity and patience. Gödel's limits also highlight the interplay between simplicity and complexity. Basic arithmetic, seemingly straightforward, suffices to construct statements that cannot be resolved within the system. From simple rules, profound limits emerge. From clarity arises subtle mystery. Imagine reading a proof slowly, step by step. Each deduction builds upon previous ones, a chain of reasoning stretching across pages. Yet somewhere, a statement quietly evades the chain. It is consistent with all that came before, yet beyond reach. The mind pauses, reflecting on the elegant restraint of logic itself. These theorems have inspired mathematicians, philosophers, and scientists to think deeply about the foundations of knowledge. They remind us that certainty is limited, that even in the most rigorous systems, there are truths waiting beyond formal grasp. They show that the universe of ideas contains vast, quiet regions of subtlety, waiting for contemplation. Gödel's work also resonates with the human experience. Our own understanding, though powerful, is bounded. We can explore, reason, and create astonishing structures of thought, yet we encounter limits that are intrinsic, not accidental. Reflection, patience, and quiet curiosity become essential companions in navigating these boundaries. Imagine sitting with a pen, tracing axioms on paper, building proofs, and contemplating statements that cannot be proven. The room is still. The mind drifts gently through the landscape of logic. Some truths are reachable, others remain distant. Yet all exist in a harmonious, structured reality that is both reassuring and humbling. The subtlety of Gödel's limits teaches a quiet lesson, that mathematics is not only a tool for certainty, but also a mirror reflecting the edges of reason. Truth and proof are intertwined yet distinct. Some truths must be accepted, intuited, or appreciated without formal demonstration. Finally, the limits discovered by Gödel invite wonder. They reveal that the pursuit of understanding is infinite. Mathematics is not a completed map, but a landscape with peaks, valleys, and horizons. The journey through logic, proof, and deduction is meditative, expansive, and deeply satisfying, even when some answers remain out of reach. The quiet beauty of Gödel's limits lies in their paradoxical nature, certainty within constraints, structure within limitation, clarity amidst incompleteness. They encourage reflection, patience, and awe at the profound depths that lie hidden within the universe of thought. In contemplating them, we're reminded that the pursuit of knowledge is not only about reaching conclusions, but also about appreciating the subtle mysteries that quietly exist just beyond our grasp. Imagine a quiet room filled with the hum of a single computer, blinking lights, and rows of neatly stacked punch cards. A mind sits nearby, pondering the nature of computation, algorithms, and the limits of machines. This is the realm of the Turing Barrier, a profound boundary in mathematics, computer science, and logic, revealing the quiet edges of what can and cannot be computed. The story begins with Alan Turing, a brilliant mathematician of the early 20th century, who asked a deceptively simple question: can every conceivable computation be performed by a machine following a precise set of rules? To answer this, Turing imagined an abstract device now known as the Turing machine. A Turing machine is simple in principle. Imagine an infinitely long tape, divided into squares, each square able to hold a symbol 0, 1, or blank. A machine reads one square at a time, follows a set of rules, writes a new symbol, moves left or right, and repeats indefinitely. Despite its simplicity, this abstract machine can simulate any algorithm, no matter how complex, given enough time and tape. Turing asked whether there exists a universal procedure that could determine, for any given program and input, whether that program would eventually stop or continue forever. This is known as the halting problem. At first, it might seem that such a procedure could exist. After all, programs are finite sets of instructions. Could not a machine examine them carefully, step by step, and decide their fate? The answer is astonishing no. Turing proved that there is no general algorithm that can solve the halting problem for all possible programs and inputs. Some programs will forever evade prediction. No method can determine in advance whether they halt or run endlessly. This is the Turing Barrier, a fundamental limit to computation. To understand the proof, imagine a program that examines itself. Suppose a machine exists that can predict whether any program halts. Now create a new program that does the opposite of the prediction. If the machine predicts it halts, the program runs forever. If the machine predicts it runs forever, the program halts immediately. This self-referential construction produces a contradiction. No prediction machine can exist that works for all programs. This result is quietly profound. It shows that computation, no matter how precise or powerful, has inherent limits. Certain problems cannot be solved mechanically. They lie beyond algorithmic reach. Even the most sophisticated machine cannot overcome this boundary. The Turing barrier is not merely theoretical. It has practical consequences for computer science, cryptography, and software development. Programmers often encounter undecidable problems, programs whose behavior cannot be fully predicted. Engineers must design systems with these limits in mind, acknowledging the inevitability of uncertainty. Consider a modern analogy. A computer program designed to analyze all other programs for errors. No matter how advanced, it cannot guarantee perfect prediction. There will always be programs whose outcome escapes calculation. The universe of computation is vast, yet inherently incomplete. The Turing barrier also has philosophical resonance. It echoes Gödel's incompleteness theorems. There are truths and results that cannot be fully captured within formal systems. Machines, like formal systems, encounter boundaries that cannot be surpassed, no matter how logically consistent or sophisticated. Imagine watching a Turing machine in operation. Symbols flash along the tape. Steps repeat, branch, and loop. Some sequences eventually stop. Others continue endlessly, never repeating exactly, never halting. The observer can follow the path but cannot know in advance whether it will terminate. There is quiet tension in this uncertainty, a meditative awareness of limits. The halting problem also illuminates the nature of intelligence, both artificial and human. While machines follow precise rules, human intuition can sometimes anticipate outcomes that defy algorithmic analysis. Yet even human reasoning faces analogous limits. Some problems resist solution entirely, whether approached by machine or mind. Mathematically, the Turing barrier defines the edge of computability. Functions that a Turing machine can compute are called computable functions. Anything beyond this class is uncomputable. The boundary is sharp, precise, and unavoidable, yet it exists within a universe of infinite possibilities. Visualize a labyrinth representing all possible programs. Some paths lead to exits halting programs, others wind endlessly, never reaching a conclusion. The Turing barrier is the recognition that no map can reveal all paths in advance. Some routes remain forever hidden, unpredictable, and silent. The Turing barrier also shapes modern computer science theory. Complexity classes, such as polynomial time and exponential time, describe problems that are solvable within certain resource limits. Even within solvable problems, efficiency matters. Some solutions exist in principle but are effectively impossible to compute due to time or space constraints. The halting problem represents the ultimate limit, problems that cannot be solved at all. Consider cryptography. Many encryption methods rely on problems that are practically unsolvable. While not all are uncomputable, They illustrate how computational limits can be harnessed. The Turing Barrier reminds us that there are problems that are fundamentally beyond algorithmic reach, whether simple or complex, abstract or practical. Reflect on the philosophical dimension. The Turing Barrier is a quiet meditation on the nature of certainty, knowledge, and limits. Even in a universe governed by precise rules, there exist questions that cannot be answered mechanically. This is not a failure. It is a revelation of subtle structure, a boundary that defines possibility and invites reflection. Imagine tracing the steps of a Turing machine with your mind. Each instruction is clear. Each movement is predictable, yet the ultimate outcome, the halt or endless continuation, may elude prediction. The quiet tension of this unknown outcome is a source of wonder and contemplation. The Turing Barrier also connects to artificial intelligence. While machines can perform incredible feats of calculation and pattern recognition, some questions remain unanswerable. Even as computers surpass human capabilities in many areas, there are limits embedded in the very logic of computation, invisible yet unavoidable. In a sense, the Turing Barrier is a reminder of humility. It shows that knowledge, computation, and intelligence all have boundaries. There are problems that cannot be solved, statements that cannot be predicted, sequences that cannot be fully understood. Yet this limitation is not a deficiency. It is a natural feature of systems, quiet and profound. Finally, the Turing Barrier invites reflection on the infinite. The space of possible programs is endless. Some terminate quickly, some run forever, some hover on the edge of unpredictability. Within this vast landscape, the halting problem stands as a gentle, paradoxical boundary, a quiet line separating what can be computed from what lies beyond. The beauty of the Turing Barrier is its subtle elegance. It reveals that computation, like thought, is bounded, structured, and intricate. It encourages patience, meditation, and appreciation for the profound boundaries of possibility. Even in impossibility, there is a quiet order, a meditative reflection on the limits of logic, the nature of machines, and the infinite landscape of computation itself. This is the Turing Barrier, a paradoxical silent frontier in the mind of mathematics and computation, inviting us to explore, reflect, and quietly marvel at the limits and possibilities woven into the fabric of reasoning itself. Imagine standing at the edge of a vast ocean at night. The water stretches endlessly in every direction, merging with the horizon, where sky and sea blend into a quiet darkness. You cannot see the end, and yet you sense a subtle order in the gentle waves and patterns of moonlight. This is the feeling of quiet infinity, a meditation on the endless, the immeasurable, and the subtle beauty of the infinite in mathematics. Infinity is one of the most profound concepts in mathematics. It is not simply a very large number. It is a concept that defies counting, measurement, and complete comprehension. When we speak of infinity, we speak of something unbounded without limit, stretching endlessly in space, time, or quantity. Yet within this endlessness, mathematics finds structure, rules, and quiet patterns. Consider the natural numbers, 1, 2, 3, 4, and so on. They continue forever. No matter how far you count, there is always a number greater. Infinity is embedded in this sequence. It is a horizon that can never be reached, no matter how patient or persistent we are. Yet the numbers themselves form a perfectly ordered set. Each number has a successor. The sequence is unending, yet structured, calm, and predictable. There are also different sizes of infinity. Mathematicians discovered that the infinity of whole numbers, called countable infinity, is smaller than the infinity of points along a line, known as uncountable infinity. Imagine a line segment. No matter how short, there are infinitely many points between its ends. You cannot count them, even in principle. This infinity is larger, more subtle, and deeply fascinating. Consider the sequence 1/2, 1/4, 1/8, continuing forever. If you sum these numbers, the total approaches 1. Infinity is present in the process, endlessly adding terms that shrink ever smaller. Yet the sum converges to a finite limit. Infinity, in this sense, is quiet, structured, and gentle, not chaotic or overwhelming. Now imagine infinite sets interacting. Pair each natural number with a point on the line segment. Even though there are infinitely many numbers and infinitely many points, they belong to different kinds of infinity. The natural numbers are discrete, countable, and individually distinct. The points on the line are continuous, uncountable, and seamlessly connected. Infinity is not a single simple idea. It is nuanced, layered, and deeply subtle. Infinity also appears in geometry and calculus. A line can extend endlessly in both directions. A curve can approach a limit without ever reaching it, and the sum of an infinite series can yield precise finite values. Imagine a curve gently approaching a horizontal line, never quite touching it. This is the notion of a limit, a way for mathematics to capture the infinite in a calm, rigorous manner. The curve stretches endlessly, yet its behavior is quiet, predictable, and serene. Consider Hilbert's hotel, an infinite hotel with infinitely many rooms. Even if every room is occupied, new guests can always be accommodated. Infinity allows for counterintuitive possibilities. A hotel full can still have space. The paradox is not chaotic, it is structured, surprising, and deeply meditative. Each room, each guest, each step in the process follows precise rules, revealing hidden patterns in the endless. Infinity also guides our understanding of space and time. Imagine traveling along a line that extends infinitely in both directions. No matter how far you go, there is always more distance ahead and behind. Motion, measurement, and thought can proceed endlessly. Infinity is a horizon that invites exploration without ever overwhelming the traveler. The quietness of infinity is also present in mathematics through fractal structures. Imagine a coastline, a tree branch, or a snowflake. Zoom in repeatedly, and the pattern continues endlessly, revealing self-similarity at every scale. Infinity here is visual, tangible, and gentle. The endless repetitions are not chaotic, they are intricate, harmonious, and meditative. Infinity also appears in functions such as 1 divided by x as x approaches 0. The value grows without bound, yet mathematics allows us to describe and reason about this growth precisely. Infinity is captured in limits, sequences, and functions, demonstrating that even the unbounded can be understood, structured, and quiet. Consider time as infinite. Moments pass, one after another, without end. Past and future stretch endlessly, yet each moment is distinct, measurable, and ordered. Infinity in time is subtle. It is not a rush, but a continuous unfolding, a gentle horizon that frames experience without constraining it. Infinity also challenges intuition. Think of the set of all fractions between 0 and 1. There are infinitely many, and yet they are densely packed. Between any two fractions, another fraction exists. This creates a quiet, intricate web of numbers, each point distinct, yet all part of a seamless continuum. Infinity, in this sense, is not overwhelming. It is delicate, nuanced, and meditative. Mathematicians also explore infinite dimensions, spaces with unending coordinates. Imagine an abstract landscape where every direction opens into another, endlessly. Despite the unboundedness, rigorous rules govern the relationships between points, distances, and structures. Infinity becomes a canvas for calm, precise exploration. Even in probability, infinity plays a subtle role. Consider infinite sequences of coin flips. The possibilities are endless, yet patterns, laws of large numbers, and statistical regularities emerge. Chaos and infinity coexist with order, forming a quiet balance that mathematics can describe and embrace. Philosophically, infinity invites reflection. It asks us to consider the limits of thought, perception, and imagination. We cannot fully grasp infinity, yet we can approach it gently, explore its patterns, and appreciate its elegance. Infinity is not an adversary, but a companion in contemplation, stretching our minds while calming them with subtle order. Imagine tracing an infinite sequence of numbers or points with your mind. Each one is distinct, yet part of a larger pattern. Each step is small, yet contributes to the endless structure. Infinity becomes a gentle meditation, a quiet, infinite rhythm, a delicate interplay of order and endlessness. The beauty of quiet infinity lies in its paradox, endless yet structured, unbounded yet approachable, incomprehensible yet intimately connected to simple numbers, sequences, and shapes. Infinity teaches patience, reflection, and the ability to appreciate subtle patterns without requiring completion or finality. Visualize a horizon where numbers, lines, and moments stretch endlessly. Each point is precise, each step is ordered, yet the horizon recedes without end. This is the quiet infinity of mathematics, a place of calm, subtle wonder, infinite exploration, and gentle reflection. In contemplating quiet infinity, we encounter the infinite not as chaos, but as structured serenity. It reminds us that the endless is not threatening but meditative, that infinity is not a void, but a landscape of subtle order, and that the mind, guided by patience, can wander endlessly without fear, discovering harmony in the infinite expanse of mathematics itself.